So when we have two edge dislocations which are slipping along the same glide plane, if they are of the same sign, then when they come into close contact with each other, due to these compressive strains, the stress field associated around the extra half plane, which is squeezed between the atomic layers, they will repel each other. And likewise, below the extra half plane, below this dislocation core, we have tension stress field. And the strain associated with these results in these two repelling each other, and this can be seen in the bubble raft. Okay. So another scenario we can have is when we have two edge dislocations of equal magnitude and opposite sign. That is, their Burgers vectors are equal but opposite in direction. And when they're coming into close contact with each other on the same plane, they will attract each other and could potentially join and remove both. They attract because of the opposite stress fields associated with them, this one being tension, compression, tension zone here, compression zone. Another scenario is when we have edge dislocations on separate planes, and these can act to attract each other in this sign convention because one will impose a force on the other. And so what we can have in that scenario is two edge dislocations on separate glide planes which attract each other, and as they move through the structure they'll follow each other. If we have another edge dislocation on the same glide plane as this, there's repulsion, as explained earlier, between the two. So this, even though this one is being attracted by this, just the same as this is being attracted by this will not line up because of the repulsion associated between these two. So we could have many others below here which would all line up and follow each other as they move through the structure. If we have two edge dislocations on nearby but separate planes which are attracted to each other, it's more than possible that they will join and both annihilate. That is, the two half planes will join and form a single plane. When we have a substitutional impurity atom, that is represented in the bubble raft model as a bubble of a larger size, this can interfere with the movement of dislocations, as the dislocations will get to this point and the extra half plane won't be able to migrate or climb across that dislocation due to the high energy barrier associated with that movement. So what we see in the bubble raft model is edge dislocations coming and getting locked around this substitutional impurity, i.e. a larger bubble. So another movement of dislocations we can find is dislocation climb. This is modelled when a vacancy migrates through the structure by solid state diffusion, one at a time, until it eventually reaches the base of the extra half plane of atoms, or replace the bottom atom in that, and The net result of this is that the whole extra half plane, and hence the dislocation running perpendicular to this, the dislocation line, will move up 1 unit. So this is a thermally activated process, and it's important for metals undergoing creep deformation. It's not really seen in the bubble raft in the practical, probably because of the strong surface tension and the cohesive forces between the bubbles and the high energy barrier associated with the vacancy diffusion. While dislocation climb was not visible in my bubble raft practical, I did see extra half planes, the edge dislocation running here, remove vacant sites, as when these dislocations move and come into contact with a vacant site, this will move and remove that vacant site as it joins to the base of that dislocation line.